Energy saving in Pharmaceutical HVAC Design. An appendage to Cleanroom Design, a complete guide. Introduction. The earliest drug stores date back to the Middle Ages. Most of today's major companies were founded in the late 19th and early 20th centuries. After the discovery of insulin and penicillin, the pharmaceutical industry utilizes many types of heating, ventilating and air conditioning, HVAC, systems, for applications ranging from bulk product manufacturing, research and development. In every pharmaceutical, the facility, the HVAC system plays an important role in ensuring that the environment is suitable for personnel comfort, dust and bacteria control, safety and product integrity. The pharmaceutical facilities are closely supervised, which requires manufacturing companies to conform to GMP, good manufacturing practices. What is GMP? GMP refers to the Good Manufacturing Practice regulations, which have the force of law and require that manufacturing, processes and packagers of drugs, medical devices are to take proactive steps to ensure that their products are safe, pure, and effective. The GMP for HVAC services embraces number of issues such as a. Fine selection of building materials and furnishes. b. Flow of equipment, personnel, and products. c. Determination of key parameters like temperature, humidity, pressures, filtration, airflow parameters. Classification of clean rooms. It also governs the level of control of various parameters for quality assurance, regulating the acceptance criteria, validation of the facilities. HVAC has the highest contribution to the overall energy spent in a building. In a standard pharmaceutical facility, it can consist of up to 60% of the consumed energy. Optimizing the energy management in HVAC can provide substantial savings in terms of operating cost, and can also reduce global warming. The following are a few design approaches on energy saving in pharmaceutical HVAC design and how to reduce energy consumption. Design approach. Approach 1, aim for NZEB, net zero energy building. The facility constructed must be nearly zero energy building. This can be achieved by using energy from renewable sources, produced on-site or nearby, and adopting passive cooling methods. Approach 2, use LEED tools to make pharmaceutical buildings sustainable. LEED, Leadership in Energy and Environmental Design, is a green building certification process used worldwide. It is a rating system for the design, construction, operation, and maintenance of green buildings, that promotes efficient use of resources and environmental sustainability. Approach 3, optimize air change rate. Each clean classification has an air change rate. The air change rate table below shows the normally followed air change rates for different grades of clean rooms. Clean room air change rate should take into account the anticipated activity within the clean room. Example: a clean room with ISO 8 classification and a capacity for 100,000 particles per cubic foot, may employ an air change rate of 15 ACPH, given its low occupancy, low particle generation process, and positive pressurization, relative to nearby less clean spaces. b. While the same clean room having high occupancy, frequent in/out traffic, high particle generation process or neutral space pressurization will probably need 30 ACPH. The recommended air change rate is a range which is anywhere between 5 to 48 for Class 8 clean room. Please note that energy consumption increases as per ACH increases. Optimal ACH depends on rate of particle generation and particle migration. By increasing ACH rates, you can only achieve the classification faster, and reduce the recovery time. It is a wrong assumption that, by increasing the air change rates, you will get a better quality of air. This is only partially true. Effects of filter air change rate, FACR. 1. Lower air change rates result in smaller fans, which reduce both the initial investment and construction cost. 2. Fan power is proportional to the cube of air change rates or airflow. A reduction in the air change rates by 30% result in power reduction by approximately 66%. 3. Lower airflow may improve actual cleanliness by minimizing turbulence. 4. A 20% decrease in FACR will enable close to a 50% reduction in fan size. 5. ACR reductions are also possible when pharma cleanrooms are unoccupied for a long time. Human occupants are the primary source of contamination. So once cleanroom is vacated, lower air changes per hour are possible, allowing for setback of the air handling system. 6. Setback of the air handling system fan can be achieved by manual setback, timed setback. Use of occupancy sensor or by monitoring particle counts, and controlling airflow based upon actual cleanliness levels. Setback of an air handling unit. The setback of an air handling system refers to a temporary adjustment in the system's operating parameters, such as temperature or airflow rate, to conserve energy during periods of low occupancy or reduced need for conditioned air. This may involve reducing the temperature set point, decreasing the airflow rate, or shutting down the system entirely for a period of time. The goal of a setback is to reduce energy consumption and associated costs, without compromising indoor air quality or occupant comfort. However, it's important to note that prolonged or frequent setbacks may lead to issues such as increased energy consumption during recovery periods or reduced indoor air quality due to insufficient ventilation. 7. Best practice for FACRs is to design new facilities at the lower end of the recommended FACR range. Once the facility is built, monitoring and controlling based upon particle counts can be used to further reduce FACRs. 8. Variable speed drives should be used on all recirculation air system for airflow adjustment, to optimize airflow or account for filter loading. Approach 4. Demand-controlled filtration. By utilizing variable speed fans, that are often incorporated into recirculation systems, it is possible to achieve significant energy savings, and improve energy efficiency. Reducing airflow is an effective method for achieving this, as there is a cubic relationship between fan energy and airflow, meaning that even a small reduction in airflow can lead to substantial energy savings. Methods. Optimize airflow for best contamination control, by real-time particles monitoring and automatic control of the recirculation system. Recirculation airflow can be controlled in various ways. 1. Use of timer or scheduling software, to lower airflow at times when the clean room is unoccupied and with minimum process activity. 2. Use of occupants sensors, to lower airflow when people are not present in the clean room. 3. Use of particle counters to control airflow in the room based on real-time cleanliness. However, system pressurization is an important factor implementing airflow reduction strategy. It is important to note that makeup air system and exhaust system will continue to operate at their normal levels. Approach 5. Dual temperature of chilled water loops. Standard cleanroom chiller plant design provides chilled water at temperature of 39 to 42 degrees Fahrenheit. For dehumidification, chilled water at 42 degrees Fahrenheit is required. For sensible cooling, chilled water at 55 degrees Fahrenheit would suffice. A majority of cleanroom chilled water requirements are best served by medium temperature 55 to 70 degrees Fahrenheit chilled water. Clean room facilities need low temperature water only to handle peak outside air loads, which occur only 2 to 5% of the time in a year. Typically, heat exchangers and or mixing loops are used to convert the low temperature energy intensive chilled water into warmer chilled water temperature for sensible or process cooling loads. So, by having dual chillers, one dedicated for providing chilled water at 42 degrees Fahrenheit and another at 55 degrees Fahrenheit. About 20 to 40% of chiller energy can be saved. Dual chiller installation. Approach 6, Exhaust optimization. All air exhaust from a clean room has to be replaced by filtered makeup air. For a clean room facility operating 24 hours a day, costs for exhaust air range is substantial. So, when determining the appropriate ventilation system for a clean room, it is recommended to rely on direct measurements rather than on estimates and assumptions. Proper optimization of exhaust flow rates results in substantial energy savings. Approach 7, Use heat recovery system. Fresh air injected into the clean room is taken from the outside environment. So, it carries a lot of heat along with it. Now, if this fresh air is cooled by the cold exhaust air exiting the clean room, a substantial amount of the heat load can be reduced. This then results in a considerable amount of energy saving. This heat exchange between the hot incoming fresh air and the exiting cold exhaust air is done by a heat recovery wheel. Heat recovery wheel. A heat recovery wheel, also known as an energy recovery wheel or enthalpy wheel, is a device that is used to recover heat from exhaust air and transfer it to incoming fresh air in a building's ventilation system. It consists of a rotating wheel, made of a material with high thermal mass and low thermal conductivity, such as aluminium or synthetic fibers. When the wheel rotates, it alternately passes through the warm exhaust air stream and the cool fresh air stream. The heat from the warm exhaust air is absorbed by the wheel, which then transfers that heat to the cool fresh air as it passes through. This process is known as a counterflow heat exchanger, as the two air streams flow in opposite directions, maximizing the amount of heat transferred. Heat recovery wheels are highly efficient, and can recover up to 80% of the heat from exhaust air. This makes them an effective way to reduce energy consumption and lower heating and cooling costs in buildings. Cold exhaust air is done by a heat recovery wheel. Heat recovery wheel installation. Approach 8, Fan filter units. The HVAC system in pharma clean rooms may consume 50% or more of the total clean room energy, and fan energy contributes over 50% of HVAC energy. The use of FFUs is becoming more and more popular, since they are modular, portable, easier to install, controlled, and monitored to maintain filtration. Fan filter units are generally used for targeted air filtration of small areas. These FFUs with EC plug fans can substantially reduce energy consumption. Approach 9, Use of high-efficiency fans. The EC, electronically commutated, plug fans should be used. An EC fan has a brushless permanent magnet DC motor with inbuilt electronics for controlling a fan rotor. The motor efficiency class is IE5. The only problem is that a single fan cannot provide the high static pressure required in pharmaceutical application. However, the solution is providing a fan array in parallel, which also gives redundancy in cases of failure of one of these fans. Approach 10, Low pressure drop systems. Fan energy accounts for 20 to 40% of total clean room energy used. Fan energy use is directly proportional to the pressure drop that the fan is pushing air through. Strategies for lowering the pressure drop includes: A. Lower face velocity air handling units. B. Low pressure drop filters. C. Optimized design of ducting and air pattern. Other benefits of low pressure drop system are less noise, more effective dehumidification, and better filter effectiveness. To reduce the pressure drop, it is recommended to maintain the filter face velocity of 250 to 450 fpm range. Approach 11, Use of many environments. Many environment is a localized environment by an enclosure, to isolate a product or process from surrounding environment. The advantages in using many environments are following. 1. Many environments may create better contamination control and process integration. 2. Many environments maintain better contamination control by better control of pressure or through use of unidirectional airflows. 3. Many environments may potentially reduce energy costs. This is because spaces that do not require clean environment can be easily avoided. 4. Use of fan filter modules, FFUs, with EC plug fans is commonly used. This is an energy-efficient system with low noise levels. Image of a mini environment. Approach 12, Filter Selection. Most of the pharmaceutical facilities require HEPA filters, which have a large pressure drop. So it is essential to pay attention to filter selection, to save an important amount of fan energy, to compensate for the filter pressure drop. When selecting a HEPA, high-efficiency particulate air, filter, there are several factors to consider, including the size of the filter, the efficiency level, and the application for which it will be used. Here is a table that can serve as a general guide. The pressure drop of a HEPA filter is primarily a function of its resistance to airflow, which is influenced by the filter's thickness, and other design factors. The pressure drop is the amount of pressure needed to push air through the filter media, and it is affected by the filter's thickness, fiber diameter, packing density, and other factors. A 2-inch thick HEPA filter has a higher pressure drop than a 4-inch thick HEPA filter. This is because to achieve the same filter efficiency, the same amount of media has to be packed in lesser space, which increases the packing density. As a result of this, the airflow resistance is higher, and more pressure is required to push the same amount of air through the filter. Here is a table comparing the thickness and pressure drop of HEPA filters for different applications. Approach 13, Variable Pumping Systems. At present, the majority of water distribution systems are designed with variable secondary chilled water pumps. These pumps use VSDs to regulate loop pressure as per the demand of all terminal units, thereby resulting in significant energy savings. Approach 14, Maintenance of clean rooms. Maintaining clean rooms can be an energy-intensive process, due to the need for constant air filtration and temperature control. Here are some steps that can be taken to reduce energy consumption, while still maintaining the cleanliness of the room. 1. Assess the current energy usage. Before implementing any changes, it's important to understand the current energy usage of the clean room. This can be done by conducting an energy audit or working with an energy consultant. This will help to identify areas of high energy consumption and potential opportunities for improvement. 2. Optimize the air filtration system. The air filtration system is one of the main energy consumers in a clean room. By optimizing the system, it's possible to reduce energy consumption while still maintaining the required level of cleanliness. This can be done by selecting the most energy-efficient filters, reducing the airflow rate, and using variable speed drives on the fans to control the airflow. 3. Implement energy-efficient lighting. Lighting can also be a significant energy consumer in a clean room. By using energy-efficient lighting systems such as LED lights, it's possible to reduce energy consumption while still maintaining the required level of illumination. 4. Control the temperature and humidity. Maintaining the required temperature and humidity levels in a clean room is essential to prevent contamination. However, this can also be energy intensive. By using energy-efficient heating and cooling systems and implementing temperature and humidity control strategies, it's possible to reduce energy consumption while still maintaining the required levels. 5. Use occupancy sensors. Occupancy sensors can be used to turn off lights and reduce airflow rates when the room is not in use. This can significantly reduce energy consumption while still maintaining the required level of cleanliness. 6. Implement a maintenance plan. Regular maintenance of the clean room equipment and systems is essential to ensure they are working efficiently. This includes: A. Regular filter replacements. B. Checking for air leaks. C. Cleaning of HVAC systems such as cooling coils, pre-filters, air-cooled condensers, water-cooled condensers, cooling tower fills and sump. Conclusion. Minimizing energy consumption in a pharmaceutical HVAC system can be challenging, due to the need to comply with GMP requirements, and the biological containment of the facility. Despite this, various design approaches have been identified, and proven effective, in meeting the requirements of clean room facilities, while also reducing power usage and costs. Disclaimer. The information contained herein has been obtained from very reliable sources, extracts from the internet and personal experiences of the author. The author disclaims all warranties to the accuracy, completeness, or adequacy of such information. The author shall have no liability for errors, omissions, inadequacies in the information contained herein and interpretations thereof. The author, and all those who assisted in preparing this tutorial, shall not be responsible for loss of any kind, whatsoever, sustained by any person who relies on this material. Every effort has been made to trace the owners of the copyright material included in this presentation. The author would be grateful for any omissions brought to his notice for acknowledgements in future editions. The material and communication methodology in this presentation is copyrighted. No parts of this presentation may be reproduced, stored, or distributed in any form or by any means either on paper or electronic media, unless authorized by the author. The author. The author, Arvind Dhawan, is a mechanical engineer with specialization in air conditioning with over 45 years experience in air conditioning and utility domain. Currently, he is a subject matter expert and certified lead trainer, Level 6 with Electronics Sector Skills Council of India, ESSCI, under the Ministry of Skill Development and Entrepreneurship Government of India, and a visiting faculty with ISHRI. He has contributed to the following: Handbook for Technicians by ISHRI, Multi-Skill Technician Handbook by CARE, Voltas, Trainers PPT, FTAC for ESSCI, App Contents FTAC for ESSCI, Revamping and refurbishments of the course materials for ISHRI. Several courses on multimedia platform available online on https://sbgblv.com. End of the tutorial. We hope that this program has helped you in understanding the energy saving in pharmaceutical HVAC design. Thank you for being a part of this learning process.